This is the code for the PM2008 that we worked on last time, and this is the code we worked on when we were dealing with serial communication before. I will organize the code for this packet and the code I use for PM2008 Live so that we can configure the PM2008 sensor data into packets and send it to the PC. First, I will save this document under a different name, specifically calling it PM2008 packet, which is chosen to reflect the year and type of data it contains. For now, I will just copy the packet files exactly as they are. And due to the fact that there is a significant amount of code this time, I will be providing this code using the following shortened address below the video description after I upload the video. The basic configuration, which is crucial for the system's seamless operation, will meticulously follow the comprehensive packet structure. However, for the time being, I will carefully and systematically organize the command, even if it's just a single one, in the following manner. PM2008. Later on, if things go well, we could expand the commands to include the PM2008 carbon dioxide sensor or a composite sensor. In this state, there is currently, as of now, only one get PM2008, but I have specifically modified it like this, and I have made changes to the packet side as well, in particular on the packet side. Next, I will modify this part so that it reads and sends the sensor values every 5 seconds. If later I want to change the cycle to 1 second or 10 seconds from the PC side, it would be cumbersome to modify the firmware each time. Therefore, I will complete the firmware to operate in a variable manner, allowing it to send data only when requested. This way, the Arduino code remains unchanged, and the sensor data will be sent only when requested from the processing PC. In our previous discussions about serial communication, we mentioned the roles of sender and receiver. However, in this case, the roles are not strictly separated. The system will check the packets coming from the PC, and it will only send the requested data when a request packet is received from the PC. For the time being, I will leave this particular section as it is, without making any changes, and plan to organize and arrange it in a more structured manner later on. In this process, I will first undertake the task of executing the initial steps, which involves pirating the kit. This is a crucial step that sets the foundation for the subsequent actions. After completing this, I find myself uncertain about the buffer's role and its implications. To address this, my first course of action will be to ensure that the memory is securely allocated and managed with the buffer. This step is vital to prevent any potential data loss or corruption. Following this, I will proceed to secure the RX buffer, which is essential for maintaining the integrity of the data being processed. As demonstrated in the accompanying diagram, the next step involves setting up the IDX button. This button serves as a confirmation mechanism when data is received, ensuring that the data is accurately captured and processed. There is also a consideration regarding whether we should fragment the data. Although at first glance, this may not seem to hold much significance, it is a precautionary measure that could prove beneficial in certain scenarios. Therefore, I will include this step in the process for now. However, I remain open to the possibility of removing it later if it proves to be unnecessary. This approach allows for flexibility and adaptability in the workflow, ensuring that we can respond to any changes or new information that may arise during the course of the project.
Next, this is the receiver side, where we did the software serial on the other side, but the hardware serial is the same. So, the serial is handled in the box. Where are we going now? This is a question that often arises when we are in the midst of a project or task, and it is crucial to have a clear direction to ensure success. Looking at the current setup, I have just configured it to be both real and real, ensuring that it is set to a global context. Initially, it indicated a buffer here, but I have since altered it to an RX buffer, which is now complete. Moving forward, I will need to revisit and modify the latter part once more to ensure everything aligns perfectly. At this stage, it is essential to verify whether a packet is incoming. This involves reading the byte and, similar to our previous communication protocols, checking the STX, examining the LAN, and confirming the validity of both the LAN and the length. Regarding the command, it is expected to be dmval, correct? This is a critical step in ensuring that the system functions as intended, and it is important to double-check all parameters to avoid any potential issues. By doing so, we can maintain the integrity of the system and ensure that all operations proceed smoothly without any unexpected interruptions or errors. This meticulous approach is vital in maintaining the overall efficiency and reliability of our processes, and it underscores the importance of thorough verification and validation at every stage of the project. Right now, it's a limitation, which means that there are certain constraints or restrictions in place. However, later on, just in case it increases, I've added it here as a precautionary measure to ensure that we are prepared for any potential changes or escalations. Then, we proceed to check the real end of the data, which involves verifying the actual conclusion of the data stream to ensure accuracy and completeness. Once the real end comes out, we use ID focus, a method that allows us to concentrate on specific identifiers to determine if the number of packets that can be processed is sufficient for our needs. If it is, we then check if the ETS, or estimated time of success, is correct, ensuring that the timing aligns with our expectations. After confirming that the packets have been received properly, which involves verifying the integrity and completeness of the data packets, we retrieve the data length and CMD, which are crucial for further processing. Finally, for 2008, let's start by setting PM2008's request rank to 0, which is an initial step in prioritizing requests and managing the workflow efficiently. In this process, you should disregard minor details, such as turning the system on and off. Instead, focus on initiating the transmission of sensor data. This involves removing any previously existing data entries to ensure that only the most current and relevant information is being sent. By doing so, you streamline the data flow and enhance the accuracy of the information being processed. This is the essential step that needs to be implemented here, ensuring that the system operates efficiently and effectively. Let's take a closer look at the sender's role in the communication process. The sender initiates the data transmission, ensuring that the information is correctly packaged and sent to the receiver. A key part of this process is the first byte of the data packet, often referred to as the error byte. This byte acts as an initial check to verify that the data is being sent correctly. It serves as a preliminary safeguard, allowing the system to detect any immediate issues with the data before it is fully transmitted. Understanding the function of this byte helps us appreciate its contribution to the overall reliability and efficiency of the data transmission process. The sender must carefully manage this aspect to prevent errors and ensure successful communication. This involves not only sending the data, but also monitoring the process to quickly address any potential problems that may arise during transmission. And if it's 0, then there is no error. And if it's 1, do it this way. So now, if you read the sensor value via I2C, and there is an error. Then at that point, basically add 1 to the first side here. And then, essentially, in this particular case, as you can see, in this scenario, add 1 to the first side here, and then, like this. When the process of reading sensor values through serial communication fails, a specific packet is dispatched to signal this issue. This packet acts as an alert, notifying the system of the failure and ensuring that appropriate measures can be taken to address the problem. If the reading process is successful, the system continues without interruptions or delays in file synchronization. This is because the synchronization process, which was previously dependent on the successful reading of sensor values, no longer requires additional waiting time. The system's efficiency is maintained as the need for delay has been eliminated, allowing for seamless and continuous operation. This improvement ensures that the system remains responsive and efficient, even in the face of potential communication failures. I will do it this way. Now, I will place the data into the data, carefully, and send it. In this case, D0 will eventually be 0, and I will put D1 and the others in order as planned. Let's take another look in a systematic manner. Now, I have loaded the packet library and declared the buffer settings to activate the memory in advance, in case there will be logic related to receiving a lot of data on the Arduino side later. There isn't anything specific to check regarding data here, but I will check it. Then I will use serial available to see if there are any incoming packets. If there are, I will read the bytes and accumulate them in the buffer. I will check the STX, verify the LAN, check if the LAN is valid, and then check if the command is valid. Depending on the symbols, I might not check the command here and could verify it later after gathering everything. Then, while continuously accumulating in the buffer, when it is time to parse, I will check if the ETX has come in and perform the check command we created, removing the comments to verify its validity. If it is not valid, I will break out of the process. Then the data. To begin with, you need to get the data range and the command. Once you have these, the first step is to use the getData function to obtain the necessary data. It's important to note that an error might occur at this stage if the data range happens to be 0. I almost made a mistake there once, so be cautious. Now, when the command issued is PM2008, it is generally assumed that no data is sent from the PC side. This assumption is based on the typical behavior observed when this specific command is issued. Therefore, in such cases, we skip the usual data check process and proceed to read the sensor values directly. This approach is efficient and saves time. However, if there is an error detected in the sensor, we have the capability to immediately break out of the process. This is a crucial step because it allows us to handle errors promptly. In such situations, we send a 1 to the TX buffer to indicate that an error has occurred. This is a standard protocol to ensure that the system is aware of the error. In the absence of errors, we proceed by putting 0, and then we move on to generate the packet. The packet generation process is quite detailed and involves several components. It includes the start of text, STX, end of text, ETX, the command itself, the length of the data, and a checksum. These components are essential for ensuring the integrity and completeness of the packet. When the data is added, the total comes to 6. This comprehensive process ensures that the data is transmitted accurately and efficiently.
Now that we have encountered an error, I have set it up to send a notification to the relevant team members and stakeholders.
This ensures that everyone who needs to be informed is promptly alerted about the issue, allowing for a quicker response time. Here, we will assume that the sensor values have been received correctly, and we will proceed to parse them with precision and care. Parsing involves breaking down the data into manageable parts, which allows us to analyze and interpret the information accurately. I need to refer to the data types here. As you can see, the measuring mode is not needed, and the coefficient is not necessary either. This is because the measuring mode and coefficient do not contribute to the current analysis and can be omitted without affecting the outcome. Looking at the TSI data by particle, there is nothing specific to check because they are all currently 16 bits. Since they are all sine waves at 16 bits, I will organize them one by one in order. This organization process involves categorizing each sine wave based on its characteristics and ensuring that they are aligned correctly for further analysis. By doing so, we maintain the integrity of the data and ensure that our subsequent evaluations are based on accurate and well-structured information. I am going to make the screen larger for better visibility. The current setup is no longer required, so it is important to ensure that you extend it fully and properly arrange both the low byte and the high byte. This is crucial because we are not using Visual Studio Code, which means I will need to organize it in this particular manner. By doing so, we can maintain clarity and efficiency in our workflow, ensuring that everything is in its right place and functioning as intended. This approach will help us avoid any potential confusion or errors that might arise from a disorganized setup. Then here is 34P5, and then no, right, no, right. All right, let's take a moment to carefully divide the numbers 5 and 6, and then proceed to complete this task thoroughly. It's important to ensure that each step is executed correctly and efficiently. This line is crucial, and we must pay attention to every detail to ensure accuracy and precision in our calculations. Let's focus and make sure everything is done properly, leaving no room for error. By doing so, we can confidently finish this task with the desired outcome. You say you draw TSI, which stands for Technical Sensor Integration, is a crucial aspect of our data management system. It plays a vital role in ensuring that all sensor data is accurately collected, processed, and stored. From this point, we have meticulously organized the data into various size categories to facilitate efficient data handling and processing. These sizes include 7, 8, 9, 10, 11, and 12, which are the initial set. These initial sizes are essential for basic data segmentation and management. Following this, we have sizes 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. This extended range allows for more detailed data categorization, which is crucial for advanced data analysis and processing. Additionally, we have smaller incremental sizes such as 0.3, 0.5, 1, 2.5, 5, and finally 10. These smaller sizes are particularly important for fine-tuning data management processes and ensuring precision in data handling. This organization allows for a streamlined process in handling data efficiently, reducing the risk of errors, and improving overall system performance. Now, as you can observe, the sensor data accumulates to a total of 24 bytes. However, when we factor in potential errors, this total increases to 25 bytes. This is an important consideration because errors can occur due to various reasons such as transmission issues, data corruption, or even environmental factors that affect sensor performance. If we decide to order 25 bytes, the total size will increase to 30 bytes. This increase is due to the overhead required for error correction and additional data integrity check. These checks are essential for maintaining the accuracy and reliability of the data, which is critical for making informed decisions based on the sensor data. Therefore, I am considering 30 bytes as a more robust and reliable option to ensure data accuracy and integrity. This approach not only safeguards the data, but also enhances the overall efficiency of our data management system. By adopting this strategy, we can ensure that our data remains accurate, reliable, and ready for analysis at any time, thereby supporting our operational goals and objectives.
This is how it's completed. Let's review it. I looked at the variables in advance to secure memory. TX buffer, RX buffer, IDX buffer. This is for checking the index on the RX buffer side. As we saw during our CRL communication, the rear rank is used to check the incoming data from the back, allowing us to verify the data that is coming in. Next, this is honestly something that hasn't been particularly necessary here, but considering the possibility of an increase in commands or the addition of various logic later on, it's intended for passing data from packets that come into the RX buffer. After that, this part is almost identical to what we did with serial communication. Now check the STX, then check the length and check the command. After that, accumulate the buffer until you are ready to pass. Then check the ETX to confirm its validity, and after that receive the data rank and check the command. Only if the data rank is greater than 0, extract it into the data buffer. If the command is PM2008, the sensor data is immediately available. If it is determined that there is an error, D0 is the error byte. If it is 0, there is no error, and if it is 1, there is an error. Assuming this, put 1 in the 1 byte data section. Then create a 6 byte packet accordingly and transmit it. If not, determine success here, set the success status of the first byte to 0 in the error byte section, and split the corresponding values into low byte and high byte, as shown in the diagram. We split it into low and high bytes and related TSI values. 1 to 12 for particle size, and 13 to 24 were included. This ensures all values are properly accounted for and accurately represented. Next, I added 5 bytes to the sensor data, which was 24 and 25, making it a total of 30 bytes to send the packet. We can't confirm it here right now, but we will check it on the processing side when we send the request and pass it. This time, just like when we had the previous lecture on the serial communication protocol, we will bring in the packets we created then and use the code from last time where we worked with PM2008 live. I created a process to wrap the PM2008 data in packets and send it again, combined with that. Next time we will process the packets we received, pass them, and save them back to CSV. Then I will see you next